Hello, Chem's 2 students. Mr. Keister here with you again. This is the video for Tuesday, September 15th, 2020, which is our scheduled 18th day of school for the fall semester. Always, of course, keep in mind that the dates could change for a variety of reasons, but the lessons and the order of those lessons will remain the same regardless. So let's look at today's agenda, our do now. No papers to pick up today. We're going to continue our lesson from yesterday on average atomic mass. All right, that's where we left off yesterday. Your homework for today was to complete numbers 1 through 3 only on the periodic table and atomic mass assignment. You may check your answers to those 3 problems. They are posted on the backboard and also in Canvas on the missing assignments, or I'm sorry, on the answer keys page in Canvas. Today we're going to finish that assignment and you will turn it in. All right, I will be collecting it for it. Great. You were also to continue working on memorizing the symbols of 39 elements that we went over again yesterday. Remember, after our lesson, I gave you a practice quiz to see where you stood on that. Hopefully you're ready to take that quiz today. It will happen the last few minutes of class today. So today we're going to continue the first half of Unit 2 by talking about isotopes and then going over how average atomic mass is calculated. Remember, a mass number is a definitive number for a particular isotope of an element, but the average atomic mass, which is that decimal number on the periodic table, is an average of the mass numbers of the isotopes of a particular element based on how often they occur. Kind of talked about that yesterday. We'll look at that today. So the lesson won't last very long, and you are to finish the assignment you started yesterday, and I'll be collecting it for a grade by the end of the period today. All right, it shouldn't take you long to do the rest of the assignment, just a few minutes actually. So with a short lesson and a short assignment, I'm going to be collecting that today by the end of the period. All right, not tomorrow, but today. All right, so let me get to the screen. Freeze it. And bring up my notes. There. Okay. So we talked about isotope notation yesterday. Reviewed how to do that. And so now today we're going to talk about how we calculate average atomic mass. So the size and mass of an atom. So atoms, of course, are very small, normally measured in picometers. The hydrogen atom has a radius of about 32 picometers. So the nucleus, as Rutherford proved with his gold foil experiment, is very tiny compared to the rest of the atom. If the atom was the size of a football stadium, the nucleus would be the size of a marble. All right? So again, imagine Rutherford's gold foil experiment, and he was shooting positive charged particles, alpha particles, and when they would hit the positively charged protons in an atom, which of course were found in the nucleus, that they would bounce off. Well, remember when he did that, most of the alpha particles went right through the gold foil as if it wasn't even there. Well, here's why. All right, think of the size of a football stadium and a marble, and you're trying to hit the positive charges found in the marble. All right, not too easy. All right, not too easy. So here again, Rutherford's experiment proved the nucleus is where the protons are at. The mass of the atom is also very small, and nearly all of the mass of an atom is concentrated in the nucleus. All right, average atomic mass, which is the mass of the protons and the neutrons, those are both found in the nucleus. They contain all the mass. So most of the mass of the atom, nearly all, because the electrons is like a fraction of a percent, is found in the nucleus. The proton is around 1.67 times 10 to the minus 24th grams. The neutron, about the same. They're not exactly the same, but when rounded to 3 sig figs, they are. The proton slightly larger. Right? And then the electron, 9.11 times 10 to the minus 28 grams, which is 4 decimal places smaller, not a full 4 decimal places. but certainly much, much smaller. All right. When compared to protons and neutrons, the mass of the electron is virtually negligible. You can disregard it. Since the mass of the nucleus, the protons and neutrons combined contains approximately 3,600 times more mass than the electrons do. So rather than using these extremely small numbers as the values for the mass of the protons and the neutrons, chemists instead compare the masses of atoms using simple whole numbers called an atomic mass unit, or an AMU, instead. This was brilliant because now we can say that atomic mass unit is 1 as compared to an actual mass of 1.67 times 10 to the minus 24th grams. So that certainly simplified things for us. So the mass of a proton or the mass of a neutron is equivalent to 1 AMU, or atomic mass unit. So 1.67 to the minus 24th grams and 1 AMU are representing the same amount of mass. The average atomic mass, or again the average mass number of the isotopes of an element, we also call that molar mass when we're talking about grams, all right, is the weighted mathematical average, weighted, of the masses of all the isotopes of the element. So if it's more abundant, it carries more weight, right? Meaning it's more influential on the average atomic mass. Okay, so let's look at how that is calculated. So chlorine has two isotopes, chlorine 35 and chlorine 37. All right, and remember chlorine 35. Remember how to write that in isotope notation? 35 over 17. Chlorine 37 would be 37 over 17. They both have 17 protons. All right? They both have an atomic number of 17. But chlorine 35 has 18 neutrons, and chlorine 37 has 20. All right? So there's a difference. In nature, chlorine 35 has a relative abundance of 77.50%. Chlorine 37 has a relative abundance of 22.5%. So chlorine 35 occurs more often, which would then tell you, well, probably the average atomic mass of chlorine is closer to 35 than it is 37. That's what it would tell me. Okay? Calculate the average atomic mass of chlorine. All right, so here's how you do it. You take the mass of each isotope, all right, times its percent abundance, expressed as a decimal. We're going to move the decimal 2 places to the left, all right? We're going to find that for each of them, then add together. It's a very simple way, very simple method. So we got chlorine 35, and we got chlorine 37. All right, chlorine 35 has a mass of 35. All right, that's its mass number. 35 times its abundance, expressed as a decimal, so it'd be 0.7750. No rounding. 27.125. Chlorine 37, mass number 37 times its abundance, 0.2250. And that gives us 8.325. Again, no rounding. And then we add them together. 35.450. So here we have 3 decimals. Here we have 3 decimals. Normally we'd round to 3 decimal, the fewest, right? You're adding, you round by precision. But for consistency's sake, if you scan through your periodic table, you'll see that most, not all, but most all of the periodic table average atomic masses are rounded to 2 decimal places. So for consistency's sake, and to take the guesswork out of it, that's what we're going to do too. Round all average atomic mass to 2 decimal places. or the hundredths place. All right. So with that being 0, 35.458 MUs. Don't forget to label it atomic mass units. You can't abbreviate it. All right. If you look at the periodic table for chlorine and check its average atomic mass, I'm looking right now, 35.45. Now, our calculation and what it says on the periodic table should match up. In many cases, like this one, it comes out exact. But keep in mind that the actual percentages may go out more decimal places than this, and so we could be a little bit off, but it should be very, very close. So when you make a calculation on average atomic mass, just look at the periodic table's average atomic mass for that element, and it should match up very, very close, if not exact. All right. If you're way off, you did something wrong mathematically. Absolutely. So it's a very easy and quick way to check your math work, okay? Which you should do anyway. All right. So let's go to the next one. An unknown element, element X, has two isotopes. One with a mass number of 10 has a relative abundance of 20.02%, and the other with a mass number of 11 that has a relative abundance of nature of 79.98%. So we have two isotopes, X10, don't know what X is yet, and X11, all right? So X10, its mass number is 10 times its abundance, expressed as a decimal, 0.2002, which is 2.002. Again, no rounding. And X11 has a mass number of 11 times its abundance, 0.7998, and that is 8.7978. So we add those up, and we get 10.7998. And again, if we rounded properly, we would, this is 4 decimals, this is 3, we would round to 3 decimals, all right? But again, since most, nearly all actually, average atomic masses in the periodic table are rounded to 2 decimal places, as I said earlier, that's the way we're going to do it. So that would round to 10.80 atomic mass units. 10.80. All right? Again, 2 decimal places. Or the hundredths place. What is the atomic mass? We got that, 10.80. What element is it? What's its atomic number and the name of the element? Well, if you look up on your periodic tables, I look over there, 10.80. Well, I see one over there that is 10.81, so I'm thinking that's it. All right, so that would be atomic number 5, which is boron. All right, boron. So this then actually was boron 10, and this was boron 11. All right, they were the 2 isotopes of boron. That is it for today's lesson. So again, short lesson. You are to finish the assignment you started yesterday. That shouldn't take you very long. So that again is due today by the end of the period. You'll need to turn that in if you're here. Of course, if you're home, you'll need to submit that to me electronically. And then also don't forget, we're going to, after I sign off here, the last couple of minutes of class, you're going to take your elements quiz, probably the last 5 minutes or so of class will do that. So that is it for today's agenda. So till next time, this is Mr. Keister signing off. Take care, everyone. Stay safe. Keep working hard and stick with it. Catch you next time. See ya.